Cowboy Joe here with a recapitulation of section 10.10 on machines. Your goal by the end of this video is to be able to demonstrate a knowledge of the usefulness of simple machines, differentiate between ideal and real machines in terms of efficiency, and of course analyze problems dealing with simple machines. So machines. Everyone uses machines every day. Some are simple tools, such as an axe and a nail puller. There are 6 simple machines shown in this screen. Others are complex, as a bicycle and an automobile. But machines, whether powered by engines or people, make tasks easier. So how do they do that? How do they make tasks easier? Well, they make tasks easier by easing the load by either changing the magnitude or the direction of the force to match the force to the capability of the machine or person. Now, what that means is it will lighten the load. So there's some advantages to machines. One thing we're going to talk about is called the mechanical advantage. And this is a number that tells us how much easier it would be using the simple machine to do the job compared to not using it. Imagine opening this with your fingers. Well, how many times easier would it be using the can opener? Well, in order to understand this term, this vocabulary word, we need to understand some other terms, some other definitions. This guy right here, the force being applied by the simple machine, by the tool, is called the resistance force. The hand pushing up on the simple machine. This is sort of the person working the simple machine's side. That is your effort force, the force you put on the machine. And the ratio of those two forces is called the mechanical advantage. Notice that the newtons will cancel and the mechanical advantage does not have any units. And it will tell you how many times easier it is opening that bottle with the tool compared to without the tool. So working simple machines problems, all you got to do is find the two forces. Now normally I don't bring in the customary units, but let's just imagine we have a pulley system set up with all of, I just thought of a cool pulley joke. Why do you think pulleys like their position? Huh? They're in the middle of attention. They're in the middle of attention. No, wait, it's supposed to be center of attention. Center of tension force. Screwed that up. Anyhow, you take 100 pounds. The lifting force is going to be the load. The lifting force is going to be your F sub R. And you divide it by the F sub E, which is the effort side. So you actually grab a hold of this rope right here and pull on it. That's going to be your effort side. So when you divide those two, you get the answer. So using this pulley system to lift that 100 pounds would be 3.7 times easier than lifting 100 pounds straight up. Another example could be this one, using a lever. This lever is used to pick up the 72 Newton weight. Levers have a pivot point or a point of rotation, point of the axis. It's called a fulcrum. And this lady's pushing down with 15 newtons and lifting up a 72 Newton rock. When you're working a lever, the job will be easier if the fulcrum is really close to the FR, the lifting load. So the closer you get this fulcrum to the object the object that you're lifting, the easier or less force that you're going to push down with. So when you divide those two on a calculator, you get 4.8, and what that means is using this lever to lift this load would be 4.8, almost 5 times easier than picking that up straight up all by itself. One more scenario, an inclined plane. An inclined plane is this slope right here, and this slope allows you to push heavy things up with less force. So the resistance force is the weight of the object, or let's say the cart, the weight of the shopping cart, and he's only pushing with 23 newtons to get this 36.5 Newton shopping cart up the ramp. So if you take 36.5 divided by the 23, we would get a 1.6. So it's 1.6 times easier, and that would be the mechanical advantage. So a machine can increase the force, but it cannot increase the energy or work. We say it's conserved. The input work is equal to the output work. The input work is really the work on one side, the person's side, the person touching the machine side. You take the force times the distance it moves. You got the input work. On the output work, you have the same kind of thing called the output work. The output work is the force of the load, whatever that is, maybe the weight of the load, times the distance that you move it. And they are equal or conserved. So, an ideal world, an ideal machine will transfer all the energy so that the output work equals the input work. Not always the case, though, in the real world. We lose some. We'll talk about that later. But in an ideal world, the output work equals input work. Now, the output work is on the forces. So you got force times, where's that formula? There it is. Force times distance. On the resistance side would be your output work. The input work is on the effort side of the simple machine, and it's still FD. But if we organize this a little differently and group the F's and group the D's, you got to divide both sides by FE, divide both sides by DR, and you have this new formula. And on the left-hand side, in an ideal world, the mechanical advantage would be FR over FE, and it equals DE over DR. So in an ideal world, an ideal machine would have a mechanical advantage of DE, the distances divided by the other distance. The two distances moved, effort over resistance. So you have a new formula. It's called IMA. IMA. IMA der. I'm a der. Say that 5 times in a mirror. I'm a der. That'll help you remember that equation. Just remember I'm a der. Your other formula here, Ma is free. Like she's in jail, but now she is free. Now the thing to note here is that the R is on top for the mechanical advantage and the sub E is on top for the IMA formula. Remember, I'm a der, and Ma is free. That'll keep that straight. So let's look at this equation. IMA. What is the ideal mechanical advantage? Now we did this already. We did the mechanical advantage for this pulley system. But what about the ideal mechanical advantage? If you divide those two distances, you get 4. We only had like 3.7, so it was close, but it wasn't an ideal. This is an ideal world. If there wasn't any friction, we would be able to get 4 out of this machine. And this one, we had, what do we have? I can't remember. 20 divided by 4, if we divide the distance, is 5. But before, we had 4.7 for the mechanical advantage, but we lost a little bit. Now, what about this? There's some friction going on here in this problem. If we lifted that card up 3 and moved it 9, then divide those 2, we get 3. So the ideal mechanical advantage is when you divide the distances, where the mechanical advantage is when you divide the forces. And the last time we had like 1.6. So in a fixed pulley, such as the one shown here, the two forces in the problem are equal, which makes the ideal mechanical advantage 1. So finish this sentence. The fixed pulley system is useful not because the effort force is lessened, but because the direction of the effort force is changed. You can use your body weight to jump up and grab a hold of that rope and pull that weight up.